Welcome back. In this video, we're going to begin with the conservation of energy equation we developed in the last video and make some assumptions to it to convert it into Bernoulli's equation. Now, Bernoulli's equation is the main working equation for this section of the course, and we'll have lots of experience in later videos and in examples applying Bernoulli's equation. But first of all, we need to understand where it comes from by understanding all of the assumptions that we need to apply to the energy equation in order to get Bernoulli's equation. Now, in this video, we're going to develop the true Bernoulli's equation. Now, in later videos in this module, we're going to be talking about rolling back a couple of these assumptions so that it has a little bit more general applicability. But the task in this video is Bernoulli's equation. So to develop Bernoulli's equation, we need to make a series of assumptions that we're going to list now. First, we're going to say there is no heat transfer. So there is a Q dot term in our energy equation that we're going to set to 0. So this is important to remember. You cannot apply Bernoulli's equation through something like a heat exchanger or anything where there's significant heat transfer. So no heat transfer allowed. Secondly, no shaft work. So that also means you cannot apply Bernoulli's equation across a pump or a turbine. And in terms of the equation, we'll be able to cross off that shaft work term. Also, no shear work. So Bernoulli's equation assumes frictionless flow. And that's a very important thing to remember about Bernoulli's equation, is there are no frictional effects in Bernoulli's equation at all. Also, steady state is an assumption we're going to be making. Now, there is an unsteady form of Bernoulli's equation that you might run into later on, but in this course, Bernoulli's equation is going to be a steady state equation, so we can only apply it to steady state situations. Now, in terms of the control volume that we're going to apply it to, we're going to look at quite simple control volumes in all cases, and I'm going to be talking quite a bit about this later in this video. But in terms of the impact on our energy equation, we'll be assuming a single uniform inlet and a single uniform outlet. Now, that's important because you can't take Bernoulli's equation and apply it in a situation where there's multiple inlets and exits. You can't look at a branch in a pipe or a T or something like that. There is a way to do it, but you have to be very, very careful. And certainly in this course, we're not going to get into that sort of thing. So we can only apply Bernoulli's equation if we have a single inlet and a single outlet. Also, incompressible flow. Now again, there's a compressible flow version of Bernoulli's equation, but that's not the one we're going to develop and use in this class. So density is going to be assumed constant as we go forward. Finally, constant temperature will also be assumed, and we'll see the impact of that a little bit later on when we simplify the energy equation using all of these assumptions. So we start off with our energy equation, the complete energy equation. The only simplification that's been made here is this equation uses a uniform flow assumption. So what we're going to do is go through this entire equation now and apply any of the assumptions that we listed on the previous slide. Well, first of all, there's no heat transfer, so that term is gone. There's no shaft work, so that term is gone. Frictional effects are being completely neglected, so that term is also gone. So left-hand side of the equation is 0. Moving over to the other side, remember steady state is going to be assumed. So this entire term is gone because it's the derivative with respect to time of the energy contained in our control volume. Well, steady state, so that entire thing is gone. Another assumption that we listed on the previous page is a single discharge and a single inlet. So I'm going to rewrite this equation. Notice this last term is the only thing that's left. So we're going to set the inlet equal to the discharge. So all of those terms are gone. We can drop the summations because we only have one of each. So we have this term at the inlet and that term at the exit. And we can cancel off these mass flow rates, because if we have steady flow and we have only one inlet and one discharge, the mass flow rate at the inlet and discharge have to be the same. So we can cross that off, and then we can get rid of the parentheses just to clean it up a little bit. So This is most of those assumptions, not all, but most of those assumptions applied to the energy equation. Now, this isn't quite Bernoulli's equation yet. There's a couple of other things we're going to do here, but it is a simplified form of the energy equation with no heat transfer, no shaft work, no viscous effects, and steady flow, and a single inlet and a single discharge. So if we remind ourselves what the terms are, it's important to remember this is still an energy equation. So it's still conservation of energy that this equation is enforcing. And it's saying that the three forms of that energy, the enthalpy, the kinetic energy, and the potential energy, have to be the same at the inlet and the discharge. Why? Because all of these things that would have served to change the energy have been assumed to be zero. So the sum of those three things is the same at the inlet and discharge. Now, it doesn't mean these individual things are the same, but it means when you add them up, they're the same. So that's the types of problems we're going to be looking at, is where there's an exchange of energy amongst these three things, and not some other source of energy like heat transfer or shaft work. Now, the next thing I want to talk about in this video is what control volume are we applying this to? Now, we've already said that our control volume has a single inlet and a single discharge, and that's what has allowed us to simplify this down and write it like this. But in the control volume section of the course, we made a big deal of identifying our control volume and sticking with that control volume choice. Well, we're really still doing control volume analysis here, because this really is still a simplified version of one of our conservation laws for a control volume. So I want to clarify the type of control volume we'll be applying Bernoulli's equation to. Now, in order to do that, I need to define something called a streamline. So if we have a flow, which in this case seems to be generally heading from left to right, a streamline is defined as a line in the flow that is tangent to the velocity everywhere. Okay, so the flow is tangent to the streamlines everywhere. So I've just drawn sort of three streamlines here. We could draw a whole bunch. So wherever you go in this flow, if you were to go to this spot right here, that means that the velocity at that spot is in this direction. So tangent to the streamline always. Now, one consequence of that is that there is never flow across a streamline, because that sort of contradicts the definition of a streamline, right? The flow is tangent to a streamline everywhere. That means the flow rate across a streamline is zero. There's never any flow across a streamline. So what we can do is use these streamlines to produce a type of control volume. So that introduces the idea of a stream tube. Okay? So a stream tube is a collection of streamlines. So I've shown here a stream tube that goes from one point in the flow to a second point in the flow. So it's flowing from 1 to 2. Now, exactly what this velocity field looks like doesn't matter. The flow is wandering along from left to right and up a little bit in this view. But these walls of the tube are streamlines. Okay, so a whole bunch of streamlines forming a little tube. Well, this is essentially the control volume that we're going to be using when we apply Bernoulli's equation. So if we define this as our control volume, it has one inlet right here and one exit. Now, the other thing we're going to be doing with this stream tube is making it extremely small. So taking this area and essentially shrinking it down to a point. Okay? Well, if we do that, then it's a very good assumption that all of the properties, the velocity, the density, the temperature, any other property that might be relevant, is constant across that area. So that allows us to apply the uniform flow assumption to this thing. And also, it has a single inlet and a single exit. So when we apply Bernoulli's equation, we apply Bernoulli's equation along a streamline. And you can really think of that streamline as a very, very small stream tube. So it might look something like this. I'm supposed to be wandering along the center line there, but there's point 2 and there's point 1. We're applying Bernoulli's equation along a streamline. Well, really what we're doing is applying Bernoulli's equation to a very specialized little control volume that's very long and skinny. It has an inlet at one end, an exit at the other end, and no flow across the boundaries. So when we start to do problems a little bit later on, you'll notice that one of the things we do very, very early on in the problem is identify the 2 points that we're applying Bernoulli's equation between. And typically we'll label those points 1 and 2 like we have here. There may be some reason to number them differently in a particular application, but let's just assume we're calling the inlet 1 and the exit 2 all the time. Well, the act of identifying where in my system is point 1 and where in my system is point 2, what you're doing when you do that is essentially identifying the control volume. So you're kind of still doing control volume analysis, and when you identify those 2 points, it's equivalent to drawing the control volume when we were doing conservation of linear or angular momentum. So there is still a control volume involved here, but we don't typically draw control volumes. Instead, we identify what 2 points are we applying Bernoulli's equation between. So now let's go back to our equation and make some further simplifications that we listed on the first slide. So here's our equation so far. Now notice I've dropped the I and D subscripts for inlet and discharge and replaced them with our numbers 1 and 2. Other than that, nothing has happened to this equation. So we want to go back now to the definition of enthalpy. So the first term on each side of the equation, that first contribution to this total energy. Well, enthalpy, remember, is U plus P over rho, or U plus PV in thermodynamics. Well, we have an enthalpy change here. So if we take a look at H2 minus H1, which is what we would get if we were to take this over to the other side of the equation here, H2 minus H1, by this definition, is going to be U2 minus U1 plus 1 over rho P2 minus P1. So notice here I've factored the rho out. In other words, I've assumed the density is constant. So constant density, this is the spot where we've made that assumption. If the density were changing from 1 to 2, we wouldn't have been able to make this simplification. So the density factored out, so it's constant, the same at 1 and 2. Now another assumption we listed in the first slide was constant temperature. Well, if we look at this term, if we have constant temperature and we have constant density, this delta U is 0. So that cancels off. Okay? Remember, in thermodynamics, if we have an incompressible fluid, constant density, then the change in internal energy only depends on temperature. Well, here we're also saying it's isothermal, so no temperature change. So U2 minus U1 is 0 in the problems we're going to look at. So that means that this enthalpy change up in our energy balance can be replaced with 1 over the density times the pressure change. So that's what we do in the next equation. So we take this, substitute in there. Notice we've multiplied through by density to get rid of this 1 over rho. So we now have P1 plus rho V1 squared over 2 plus rho GZ1 is equal to exactly the same thing at point 2. So this, finally, is Bernoulli's equation. So when we talk about Bernoulli's equation, that's what we're talking about. We're going to be using modified forms of this equation later for different purposes, but this is Bernoulli's equation. And it's important to remember that this is still conservation of energy, okay, but with the assumptions that we've discussed applied to it. So the first term here, pressure, is really representing the enthalpy, or at least the part of the enthalpy here that doesn't go to 0 because of our assumptions. So this is the flow work part, essentially. Kinetic energy and potential energy. So the sum of those 3 terms at the inlet and at the exit, or at point 1 and point 2, has to remain the same because all of those other things, work, heat transfer, unsteady effects, have been set to 0. So it's an energy balance between those three contributions. So same equation here. Now, this is a very common way to write Bernoulli's equation, but another very common way to write Bernoulli's equation is by dividing the entire thing by rho g. And notice it's incompressible flow, so that's constant. If we divide this entire equation by rho g, it looks like this. And we're going to be using both of these in essentially equal measure. Half the time we'll be using this one, half the time we'll be using this one. Now, practically speaking, the thing you need to be careful about, obviously, is making sure you don't mix these up. You don't have the left-hand side looking like this and the right-hand side looking like this. Or maybe just the kinetic energy term, you write like this instead of this. You have to make sure you're using a consistent form of Bernoulli's equation. So the units have to be the same in every term. Now notice when we write Bernoulli's equation like this, the dimensions of every term are length, or if we're working in SI units, they're meters. And that's easiest to see by looking at the potential energy term. It's just strictly an elevation, so as Z coordinate. Now that brings to mind another assumption that we've really made in developing this equation. We've chosen Z to be our vertical coordinate, and we've chosen Z to be pointing straight upwards. So when we define a coordinate system in our problems later on, we're sort of constrained to having Z pointing upwards because of the way we've defined potential energy in Bernoulli's equation. But notice that the units of every term in this equation would be meters. Well, when we are working with Bernoulli's equation in that form, then the word that we use to describe these different terms is head. And there are particular portions of this equation that are different forms or different contributions to the total head. All of these added together are, of course, the total head, but the first and the last term combined together are called the piezometric head. And you'll be talking quite a bit about this in one of the laboratories in the course. And this last term here, which is associated with kinetic energy, is called the kinetic head. Now in the next video, we're going to be talking about how the piezometric head and kinetic head change as we flow through various types of systems. But for now, we're just defining the sum of these two terms as piezometric head and this term as the kinetic head. All three together are known as the total head. Now before we end this video, I want to take Bernoulli's equation and apply it to this situation. So we have here an open reservoir, a large tank, and a free surface here. There's a hole in the bottom of this tank, and what we want to know is what is the velocity or speed, I guess, of the water coming out of that hole. So this is going to be our first application of Bernoulli's equation. What is the speed of the water coming out of that hole? Notice we've got G pointing downwards here. And also notice that the depth of the water above this hole is this distance h here. Well, we're going to use Bernoulli's equation to figure out the speed of the water coming out of that hole. So the first thing we want to do is identify where is point 1 and where is point 2. And remember, this is analogous to identifying what is our control volume. Well, we're going to put point 1 at the surface of this reservoir and point 2 at the exit. Now notice we're doing exactly the same thing here as when we chose control volumes. Two of the principles that we applied when we chose control volumes was, first of all, make sure the control volume choice gives you the thing you're interested in, and also put your control surface places where you know things. Well, we're following that same principle here. If we were to imagine what all the streamlines in this flow look like, realize that the water is going out of this hole and it's coming from the entire container. So the water is just slowly moving down, and as it gets closer and closer to the hole, it'll speed up, and finally be squirting out at point 2. So what I've shown here in red is a streamline in the flow. It's only one streamline. We could draw as many as we want, but we only need one. So we're going to apply Bernoulli's equation along that streamline. So you can think of that as our control volume. So this is our so-called inlet to the control volume, and this is the exit of the control volume. Now realize that I've followed those principles in choosing this control volume. I put 0.2 here because we're trying to find the speed of the water at 0.2. We want to put that point where we're interested in finding out information. Likewise, I put the other end of this streamline places where I know things. And we'll talk about the things we know at 0.1 as we begin to work with Bernoulli's equation. So, just the same diagram, a little bit smaller. Notice I've put a coordinate system on here. Z pointing upwards to be consistent with the notation that's already buried in Bernoulli's equation. But I've put Z equals 0 down at this point, at 0.2, at the hole in the tank. So here's our complete Bernoulli's equation. So we're going to begin to make assumptions to this equation. Well, first of all, in terms of the pressure at 0.1 and the pressure at 0.2 are the same. Remember, this is a free jet of water here, and it's just at atmospheric pressure. So as long as we're willing to neglect the very, very small change in pressure with elevation in the atmosphere over this distance, then we can say P1 equals P2. So that will cancel off both sides of the equation. So in this particular application of Bernoulli's equation, this particular form of energy is not contributing to any change in properties from 0.1 to 0.2. It's the same. Now the next thing we see here in Bernoulli's equation is the kinetic energy of 0.1. Well, realize another assumption we're making here is that this hole is very small compared to the cross-sectional area of the tank, which means that this level, this depth h, is going to be moving down very, very, very slowly. Okay? So we're going to assume that V1 is 0 and that the kinetic energy of this point moving down is very, very small. So if we were doing a more full-fledged problem here, what we would put in our assumption list is it's a large reservoir, or the hole is very small compared to the size of the reservoir. So the speed at which 0.1 is dropping is negligible. And this also makes it a steady problem. Well, the next thing we can say is that Z2 is 0, and we can say that just because of where we've put our coordinate system. We've put our datum, or our 0 for the coordinate system, down at 0.2. So we just set Z2 to 0. And Z1 is equal to this distance h. So the Z coordinate of the surface is just h. So when we take all of those things and apply it to Bernoulli's equation, these two terms are gone, that term is gone, this term is gone, so we can solve for this V2, and we get this. V2 is just the square root of 2gh. So what is happening here in terms of conservation of energy is potential energy, the fact that this water at 1 is at a higher elevation, is being converted into kinetic energy. So the potential energy at 0.1 is equated to the kinetic energy at 0.2. So Bernoulli's equation lets us predict the speed that the water will come out of that hole. Now remember, one of the assumptions in Bernoulli's equation is frictionless flow. So the result we've got here doesn't take into account any frictional effects whatsoever. In reality, as the water accelerates and goes through this hole, there'll be some frictional effects here. Now it depends on the exact design of this hole, how significant those frictional effects are. So the actual velocity would be a little bit less than this. So in practice, there would be a discharge coefficient that would go in front here that would take into account those frictional effects. But in terms of frictionless Bernoulli's equation, that's a quick prediction of what the flow velocity would be coming out of that hole. Now I want to point out another thing here. This is all fluid mechanics. We're using a very important equation in fluid mechanics to predict the velocity of the water coming out of that hole. What if we were to take, let's say, a golf ball and drop it from rest at this same height? And again, we need to neglect frictional effects, so we have to imagine there's no air resistance. So we're taking that golf ball or any other object that we want, dropping it from that elevation and asking ourselves, when it's down here, how fast will it be going? Well, if you went back to your GE 125 course and you did that, you would get exactly the same answer because you would be doing exactly the same thing. You'd be equating the potential energy up here at state 1, that rho g z1, with the kinetic energy down here at point 2. So you'd be equating kinetic and potential energy. You would solve for the speed of that ball as it gets down at the origin of the coordinate system. So it's exactly the same thing. Conservation of energy for a particle like that, conservation of energy for a fluid. It's not any different. Just for a fluid, we need to take into account this extra term here, which in this problem happens to be 0 or happens to be equal. So we just have our classic balance between kinetic and potential energy for an object falling from one elevation to another. So what we're going to do in the next video is look at the contribution of these three terms when flow is going through a pipe and encounters a contraction. So some of the terms change and some of them don't. And we want to start to understand what happens when we have pipe flow and the diameter of the pipe changes. So we'll see you in the next video.